In this video, we're going to discuss a common method for finding the incircle of a triangle and give an explanation for why this method works. One of the defining properties of an incircle is that this circle that is inside the triangle is of a certain size such that each edge of the triangle is tangent to the edge of the circle. There is a simple process which enables us to construct this circle. We start by picking one of the angles. Let's select the top angle, and we draw an angle bisector which passes through the opposite edge. And then we repeat that same step on another angle. Let's choose the base angle on the right. We draw a line which bisects the angle and passes through the opposite edge. But bisecting two angles in the triangle results in the two bisectors intersecting. There's one more thing that we need to do before we can draw the incircle correctly, and that is we pick any of the three edges and we draw a line that is perpendicular to that edge, but that also passes through the intersect of the angle bisectors. I'm going to do this on the right edge of the triangle. We can do this by drawing two curves that pass through the intersect. The origin of those curves must be at each end of the chosen edge. So starting with the compass point at the top of the right edge, I draw a curve that passes through the intersect, and then putting the point of the compass at the bottom end of the right edge, I draw another curve that passes through the intersect. You can see that these two curves intersect in two places, one at the angle bisector intersect and another elsewhere. And if we draw a line through both points where the curves intersect, the line is both perpendicular to the right edge and passes through the angle bisectors intersect. Let's drop in the right angle symbol and remove the curves to make things a little bit more clear. And now if we place the point of a compass at the intersect of these three lines and align the end of the compass to the point where the right edge and the perpendicular meet, when we draw the circle, all three edges of the triangle will be tangent to that circle. And that's how we can construct the incircle of a triangle. But our main reason for being here is to find out why these three intersecting lines, the two angle bisectors, and the line that is perpendicular to one of the edges allow us to accurately draw the incircle of a triangle. So now we're going to analyze the triangle and the incircle to see why this makes sense. In order to do this, we're going to use the properties of two different geometric structures. The first property is regarding tangents to a circle. There is a circle theorem called the two tangents theorem. This theorem states that if you have two tangents to a circle and both tangents originate at the same point outside of the circle, the length of both tangents are the same. That is, the distance from the outside point to the point where the line touches the circle is the same for both tangents. Now consider the triangle and the incircle. We know that each edge of the triangle is tangent to the circle. We also know that any two edges of a triangle meet at the same point. And because each edge is tangent to the circle, that essentially means that two tangents, which are just the two edges, meet at the same point outside of the circle. To make this easier to visualize, I'll show the tangent points where the edges are tangent to the circle and each vertex of the triangle, which is the point where these tangents meet. Now, if we focus on the bottom right corner, for example, we can see two lines that are tangent to the circle that meet at the same point outside of the circle. So the two tangents theorem must apply to these two edges. And that has to mean that the distance from the tangent points to this triangle vertex must be the same. I'm going to give those two lengths a label of A. But the same rule must apply to the top vertex and to the left vertex. The right and left edge of the triangle are tangent to the circle and they both meet at the same point outside of the circle. So the length from the vertex to the tangents must be the same. We'll give those a label of B. And by now you should recognize that exactly the same principle applies to the left vertex. The length of both tangents to the circle must be the same, and I'll label those lengths with a C. Next, I'm going to add in the circle center, and then we'll draw a radius from the circle center to each of the tangent points. Obviously, all of these are the same length because they are just the radius of the circle. I'm going to label them with an R. Now what we've actually done is we've divided the triangle up into several polygons. Remember that the green dot is the center of the circle, but we've divided the triangle up into 3 polygons, and if you look carefully, each polygon is a quadrilateral made up of 2 edges of length R and 2 outside edges which are of the same length. Now if for each of these 3 polygons we draw the long diagonal, that is a line between the circle center and the triangle vertex, we get an interesting result. Beginning with the left polygon, let's draw the diagonal. The polygon is now divided into 2 triangles, but you should see that these 2 triangles are identical because both have the edges C, both have the edges R, and they both share an edge, which is a line that we just drew. That has to mean that the outermost angles of both triangles must be identical because both of them are the angle between the edge C and the line we just drew, and I'll give them the value of X. Now in the polygon on the right, if we draw the long diagonal, the result is 2 triangles that have the edges R and the edges A and the edge we just drew. They are therefore identical in size, therefore their outermost angles must be identical. Both the angles are formed by the edge A and the line we just drew. So I'll label those 2 identical angles with the value Y. And by now you should understand if we add the long diagonal of the top polygon, we get the same result. 2 identical triangles because they have the same edges, B, R, and the line we just drew. So their outermost angles must be identical, and I'll label those 2 angles with a Z. We can now show why the angle bisectors in a triangle are significant. Let's remove each radius and the edge labels, and what we're left with is essentially 3 angle bisectors. But it should also be clear to you by now that the point at which the 3 angle bisectors intersect is the center of the incircle. But because all of the angle bisectors intersect at the same point, it's enough to only draw 2 angle bisectors in order to find the center of the incircle. And that's why in the process of constructing the incircle of this triangle, we used 2 angle bisectors. There is just one issue left to deal with, and that is that these tangent point marks were just visual approximations of the real tangent points. When we're trying to construct an incircle, these don't exist. So we need to have a way of finding exactly where the circle touches each edge. So let's imagine that we don't know the size of the circle yet, and we don't know where these tangent points are. How do we go about finding the size of the circle? Well, one way we could do this is by figuring out the length of the circle radius. Well, there is another circle theorem that comes to our aid, and it's the one that says that the angle between a tangent and the radius of a circle is 90 degrees. In other words, if you draw a line between the center of the circle and the tangent, and that line is perpendicular to the tangent, it must be the length of the radius. That must also mean that if you draw another line beginning at the circle center and ending at the tangent, but the angle between that line and the tangent is not 90 degrees, such as with this line, we can see that the angle between the line and the tangent is not 90 degrees, then the line cannot be the length of the radius, and you can see, in this case, this line is significantly longer than the radius. And so that means that in our case, all we need to do is draw a line that begins at the circle center and is perpendicular to one of the tangents, and the distance from the circle center to the tangent will be the circle radius. And that's precisely what we did earlier when we used 2 curves to produce a line that was perpendicular to the right edge of the triangle. Because all of the edges will be tangent to the incircle, including the right side edge, for the perpendicular line we drew, the distance between the circle center and the tangent, which is the right edge, must be the length of the radius of the triangle's incircle. All we need to do is place the point of a compass where the 2 angle bisectors and the perpendicular line meet, and place the end of the compass where the perpendicular line meets the edge or the tangent. And then when we draw the circle, that will result in an accurate incircle. And so there's a proof of why this method, where the intersect point of 2 angle bisectors and the perpendicular of one edge of a triangle, enables us to accurately draw the incircle of any triangle. Well, that's it for now. Thanks for watching.